Okay, so we've got a little bit of time. Hopefully you've gotten through sections A and B. Hopefully the math there makes sense. We're going to use that math to build the field force and basically sit there and go, okay, section A and B, we figured out what the electrons want to do or protons want to do. How are they going to move? Now we're going to sit there and tell me, okay, where is equilibrium? Where does that particle want to stabilize and not move anymore? A little bit harder. The idea is the same though. You're going to find the force of one on another, the force of the second on another, and then that is going to give us a basic for where the particle will fall into equilibrium. Now, generic definitions, Coulomb's force is a field force, meaning it gives it no physical contact. Basically, it's in an area. You guys understand this by studying magnets. Your book actually has a few good pictures when it starts in the back section of page 577, 576. Hopefully you guys understand that, but if you want more clarification, I would look there. So electric field, yes, you're going to calculate its field strength. You're probably not going to draw the field lines. Why? That's physical science. We're not going to spend time doing it. If you want to, we can, but there's not a lot of benefit in that. Now, field strength, determining what that is, we're going to spend most of our energy and effort. So electric field, basically any place where you can find an electric force. Any place you can feel force. When we talk about gravity, we made the example of, hey, look, the moon is here, the earth is here, somewhere in between, there's no gravity. Well, no, that's not true. It's a balance between where the moon is and where the earth is. If you can feel the gravity, it's there. Same idea with electric field. Basically, any electrical force, when you can test where it is an electric field. SI units, capital E, are newtons per coulomb. Newtons per coulomb. So in this case, you have field vector E. Basically, it's kind of like the first section where you sit there and say, okay, where is force on a small positive charge? So again, it's going to be small positive charge as we go through this. You'll see as we go, the equations kind of look similar. In this case, electric field strength depends on the charge and the distance. Again, you have coulombs. So electric field strength, capital E, equals Coulomb's constant, Kc again, charge producing the field, and the distance it is away. So there's your equation for this section. Whoop. And again, the cool news is, if you look at this charge, go, okay, now you see at this point, point P in the diagram, I can tell, well, okay, if I put a positive there, again, we're going to use the positive as an example, and there's a positive there. Oh, wait, that's going to push it away. But there's a negative here, so it's going to pull it this direction. Before you get into any of the numbers, positive, positive. Oh, look, it's going to push it up. Negative. Oh, it's going to pull it this way. Okay, if you can do that, you're in a step in the right direction. Now, here's the good news. I'm not looking at the math for this one. We'll do plenty of math in class. If you want to, you can jump ahead. If you want to look at the far left side of the screen, oh, look, 1, 2, 3, 4, 5, 6 slides of math. But the point is, I want to get across to a lot of you is this is what you're going to end up with. Again, it's just a matter of finding that the force of the electric field in the x direction, that's the total force. In the y direction, that's a total. Pythagorean theorem and find the angle. This is nothing hard. You guys have done it. So a lot of people get stressed out about doing the calculations. It's not that hard. It is a lot of work. Don't get me wrong, it's a lot of work, but it's not horribly bad. You've done it before. So now, field lines, stuff you should already understand. Positive, you'll see this diagram hopefully in your notes in your book. Positive charge is Q, is Q plus, it's a little red. Negative charge, negative Q, field vector. Not going to waste your time with that. Okay, so electric field. Electrostatic equilibrium. This is where it's zero. So I want to get to a point where that particle doesn't want to move. Any excess charge, outer surface. So in this case, basically an earlier diagram when we talked about you running around with a charge and touching a doorknob, excess charge in an isolated conductor, outer surface. You running around your house, you pick up static, you are conductor, conductor surface. Electric field, is just outside and is perpendicular to conductor surface. One of the cool things, we'll actually pull up the Van de Graaff. We'll see whose hair can stick up the farthest. Probably not going to be mine, just FYI. But it does lead to this whole perpendicular. Why? Because as those electrons build up on the outside, they want to get as far away from each other as possible. So that's actually the last bullet. Irregular shapes. Accumulate radius of the curvature is the smallest surface. Why? They think it's actually giving them the most space, and that should make sense to you. So, questions. Hopefully you have some. We're going to do a lot of calculations in class, and by a lot, I mean we're going to do a lot of math. The key here is you have to work together. If you don't work in class, you've got to come in and see me. If something is not making sense when we do the calculations, the one or two that we can get through in class, you've got to ask the question. Some point you're going to be working on your own. You've got to understand the math. Okay, we don't have time for a lot of examples in class. I will tell you, this is not the easiest subject, but by far it is something manageable. Again, look forward to seeing you in class.